Hello, everyone. Welcome back. My name is Václav Petříček, and I run machine learning applications at eHarmony. And I would like to tell you how we match people and how we use Hadoop to do it, we use Hadoop to deliver the best matches possible to our users. But before I do that, I would like to draw your attention to my Twitter handle here at the bottom. If you have any questions, you can tweet them at me, and I promise I will answer them after the talk, given that we have quite a few people here. So eHarmony is different than your typical dating sites. Typical dating sites are search-based. That means that you specify your criteria, and the site returns anyone who matches your criteria, right? eHarmony is different. eHarmony was founded by Dr. Neil Clark Warren, who was a psychologist and marriage counselor in Pasadena. And he was working with married couples, and many of these married couples that were coming to him were in failing marriages. And over time, he realized that very often, the two people are just fundamentally incompatible. And wouldn't it be nice if we could help people to find someone that they are not only attracted to, but they are also compatible in terms of their psychology, so even 20 years later, they would enjoy doing things together. So they set out to do some research because they had a lot of questions, right? Is it possible to predict marital satisfaction from a questionnaire or from something that you learn about a person, about their psychology? So they took a sample of a few thousand married couples, and they had them take these long questionnaires, and they assessed them how happy they are in their marriage. And then looking at this data, they actually realized that there really are some psychological traits of people that help predict long-term marital satisfaction. So, and this is how eHarmony was born in the 90s. Today, eHarmony has about 200 people, most of them based in Santa Monica, especially the tech. So about 45% of people are in tech. That includes product, matching development, front-end development, etc. We also have a very good customer care that helps our customers go through the ups and downs of dating and supports them emotionally on their journey. And then finally, if you watch TV, you might have seen one of our commercials. In fact, we have about 90% brand awareness in the online dating category. So to match people effectively, we need to solve three separate problems. So one thing is to find the people who are psychologically compatible with each other, and especially for the long term. But then, psychological compatibility is not everything. It's not sufficient. The people still need to be attracted to each other to actually get married, right? So that's where affinity matching comes in. And finally, if we know whether the two people are compatible and whether they would be interested to talk to each other, there are still a lot of choices, and we need to decide who to introduce to who and when. We want to give people enough choices, but we don't want to overwhelm them on the other hand. So this is how we do the matching, but it doesn't sound very romantic, right? So, what happened to this, their eyes met across a full room and the whole world stood still. So let's have a look here at Adam. Adam was an eHarmony user, and he's looking for a serious relationship for the whole life, right? So how would he go about that? He'll probably go to a party, let's say there is 100 people, and he looks around, and he's looking for someone for long term, but how he's going to do it? He's probably going to look around for the best looking person, to target, right? So maybe he's into brunettes, this tall, so he makes his pick, approaches her, and uses his best pickup line. And if he's lucky, then by the end of the evening, he will know where she's from, what kind of music she likes, maybe a few other things. But he will not know anything about her psychology and about the deep stuff that the psychological research shows that matters for the long-term relationships. So that's where compatibility matching comes in. To get at these deeper characteristics of the personality, we ask people, our users, a lot of questions. For example, how well does this following describe you? I try to accommodate the other person's position, right? And on a scale, on a 7-point scale, users answer that. This provides us like a very small piece of information about that person who is answering it. And in fact, we ask about 150 questions. We used to ask about 500 questions, but over time we got better at targeting these questions at the things that matter. And we managed to narrow it down. And this battery of 150 questions provides us a very good snapshot of the personality of the person. So just for illustration, to give you an idea, these questions combine, and then we get to know a certain score, how a person scores on several different dimensions. And one of these dimensions is obstreperousness. So here you see a lot of marriages. So the blue marriages are happy marriages, and the red marriages are the ones which are distressed. And you see the obstreperousness of the male on the y-axis, and then you see the obstreperousness of the female on the x-axis. And the more obstreperous person are on the right and up. And already from this data, you can see that there is some kind of a relation between obstreperousness and marital satisfaction. So these are real married couples, you know, and they have been assessed on how happy they are, how much time they spend together, how much they laugh together, etc. So if you knew the score of how obstreperous a person is and how the other potential candidate is obstreperous, you could build a very simple model that could tell you very roughly what are the chances that if they were to be attracted to each other and get married, that 20 years later they would be happy or unhappy. But there are quite a few of these dimensions because, you know, like humans, we are pretty complex beings, but we are not completely random and unpredictable. Another dimension is romanticism. So the more romantic people here tend to have happier marriages, right? And all these dimensions, and there are quite a few of them, we started with about 29, but expanded it over time, they all come together into a model that we use, and we are able to predict for any two people who are single and looking to meet someone for a long-term relationship, what are the chances that if they get married, they will be happy or unhappy. If you look at the distribution of the marital satisfaction, you might get a chart like this. So on the left, you see the unhappy marriages, and on the right side, you see the happy marriages. There is a slight bias towards a little bit more happy marriages because people who are unhappy don't stay together or don't marry really in the first place. But still, a lot of the marriages happen to be somewhere in the middle. So, and at eHarmony, we have these models that can predict whether two people, where they will be on this distribution. And as our self-imposed rule, we will never introduce to people if there is not high enough chance that they will be in this upper quartile in terms of marital satisfaction. So for every two people in the database, we will check what are their chances to be in this part of the marital satisfaction. And if there is a high chance that they will be super happy, then we introduce them. So the way it works for Adam here is that he's presented with a set of candidates, and each of them is psychologically compatible with him. So that means that if they were attracted to each other, got married, there is a very high chance that they would be very happy. So this is about the psychological compatibility, and this is how eHarmony used to be, actually. This is how it started. But not all compatible people are actually attracted to each other and interested to talk to each other. So that's where the affinity matching comes in. And affinity matching, this is, we treat it as a large-scale machine learning problem, but, and try to introduce as many people who would be interested in each other. So, you know, like, as I said, some people who are psychologically compatible might not be interested to get married, just because maybe sometimes the age difference is too big. Sometimes they live too far from each other, but other times they are interested and mutually interested here. We are interested to introduce people who will like each other, both of them, not necessarily just to show someone attractive pictures, but both of them need to be interested in each other to actually get married. So these are the matches that we like, and we try to make the highest number possible of them. And to do that, we use everything that we learn about our customers. Through the questionnaire, we know their ethnicity, we know what mobile devices they are using, are they single, divorced, widowed, what kind of religion they are. We also have the full history and the interaction, who they communicated to on the site, which is very useful to predicting future communication, etc. So just one example of a feature which is very predictive of communication is distance. Right? So here on this chart, you can see on the x-axis distance, which is on a logarithmic scale. So that fall off, actually, in probability of two people communicating to each other is actually even steeper. And you can see that after about 60 miles, it doesn't matter much how far the two people are from each other, and there is like roughly similar probability of communication between them. And people obviously prefer to talk, or are more likely to talk to people who are closer to them. So distance 0 means that they live in the same zip code. And you can see that people still talk to each other even if they are very far from each other. So here is a visualization of 1 day of communication on eHarmony a few years back. Each line corresponds to two-way communication here. The data has been aggregated to centroids of zip codes. And you can see that even intercontinental romance is happening. So there is a lot of communication happening inside the cities where there are the bright spots. But even between America, Europe, and Australia, people get talking and they actually get married. Another feature that is predictive of people being interested in each other is height difference. So on this chart, you can see the height difference represented as like the height of the male minus the height of the female. And the vertical line corresponds to the point where they are both equally the same height, right? So you can see that the highest chance of the two people being interested is when the male is about 4 to 8 inches taller, and then it falls off on both sides there. Doesn't mean that it's impossible that like two people who have the non-conventional height ratio will never be interested in each other, but just this is the empirical data from how users actually behave in the wild. So another obvious feature is like the user photos, right? There is a lot of information in the user photos about, like whether you would be interested to talk to them. So we as humans are very good at analyzing photos and extracting these subtle clues from the photos. And machines are not so good at it. So you could write a classifier that will try to classify the appearance of the person as like a trendy, hipster, classical, or something like that, but it's pretty noisy. It might do slightly better than random, but it will be very noisy. But then there are some very obvious aspects of the photo, like the size of the photo, the aspect ratio, etc. But somewhere in between are features that you can still programmatically extract and that may be meaningful to predict communication between users. So for example, you can run face detection and you identify the faces in the pictures, and then you can look at the relative size of that face that you discovered versus the whole picture. And so that gives you sort of a proxy for what kind of a shot it is. Is it a passport photo, or is it a photo that has been taken with a webcam or with a mobile phone just from very close? So here we have like 4 types of these photos. And when you look at how successful the users are in like receiving inbound communication on the site, conditional on what kind of photo they uploaded, you will see that the most success have the photos where you can see both the face and the body. Then the passport photos are doing pretty okay too, but these photos where it's taken from very close and the face gets distorted, it's not a very flattering shot. And big turnoff is if you cannot tell who it is in that photo. So this is another feature that can be used to predict whether two people will be interested to communicate to each other. And of course, there is a lot of information about the profiles. So users create their own profile, they can write about their experiences in life, what they are passionate about, and so on. And you can find features, like for example, you could look at the simple overlap in words in the two profiles, right? That would be already some signal whether they are talking using the same words or not, right? That will provide you a signal that's a little bit better than random. But as you can see here in the example, a lot of the words that overlap are sort of so-called stop words. So they don't convey any meaning, and if two people say me and my, it might not be a very strong signal whether they are made for each other. So you can get rid of these stop words, and you will be left with some words that appear less frequently. But even between these words, some of them may be more meaningful than others, right? And one technique that you can use to sort of reweight the overlap is TF-IDF, where you basically weight more words that are relatively rare in the whole corpus. So generally, that word doesn't appear in most of the profiles. But these guys just happen to have an overlap in it. So let's say that the word world is relatively rare, but they both said it, so that would contribute a lot to their mutual overlap. And then from this kind of a TF-IDF weighted overlap, you can get a feature, and you could build a very simple model, again, which would be predicting whether two people will be sending each other messages. So, and what we do with all these features that I have shown you is that we combine them, all of them, into models. So we have this information about, on about 40 million users who registered at eHarmony since the beginning of eHarmony. And we also know whether we have made some successful matches or whether the people didn't communicate on those matches. So we have this history going many years back of matches that we have done, and we know whether they were successful or not. And together, this information can be combined to train machine learned models, which then predict basically the probability that two people will be interested in each other, conditional on everything that we know about the two people. And then we can use these models. I will show you how. So how we do that is, in the training phase, we have a commodity cluster, which is running Hadoop Yarn. The data is coming from production in the form of protocol buffers, which is like Google's evolving format, which supports nested data structures. It's typed, so it supports very efficient compression, especially if you have typed data. And we have the information about, who communicated to who has been introduced to who, and also about the features of the users that we have introduced. And we need to join everything together to build like a giant table. We use Hive for this, especially because like when we need to prototype something and someone needs to step in, like all you need is like SQL knowledge, and you can run some analysis and some very quick exploratory analysis on that. And then we have this internal project called Maestro, which is a Spring Batch job, which automates this multi-stage data cleaning and data joining, and the output of this is this big table that then gets transformed using basically just Hadoop map jobs into a format that's suitable for machine learning. During this step, we use our own in-house domain-specific language, which is written in Scala. I will give you some more details in a bit. And then this output, which is suitable for the machine learning, then you can feed it to your favorite machine learning algorithms. We really like vowpal wabbit. This is a project written by John Langford, originally at Yahoo, now at Microsoft Research in New York, which is super fast online learner. So it's so fast that on your typical data sets, even like very large data sets, it will run on the laptop. However, it also has a allreduce implementation, which can run on the cluster. So it uses Hadoop as a transportation mechanism to spawn some workers on the Hadoop cluster. And then using a spanning tree communication structure, it averages the models that are learned at the different nodes. So this way it can scale to like 1 terascale feature size data sets. So once the machine learning algorithm is done with the data, it outputs some specification of a model. And then this process is sort of mirrored in production, where in production we have custom Java jobs which are doing these joins. And for efficiency and for the speed, because we need to crunch this data every night, and we need to deliver the matches so that people in the morning can go and communicate, we went through several phases of implementing this process. So the initial naive implementation, when we were using Oracle database to store the data, there was like an ETL process which was dumping this data every night, and then on Amazon in the cloud we were doing these joins. It took about 10 hours. Currently, we have this with a much larger user pool down to about half an hour, thanks to map side joins. And also thanks to the fact that all the data now lives in Voldemort-backed web services, so it's continuously updated there. And for the purpose of the joins, when we are joining, the information about who is compatible with who, so that you see here in this pairing browser service, so that's the information which users could be potentially introduced to each other. And then there is this matching user service, which has the information for each user, everything we know about them. So this gets dumped into the cluster, and then the map side joins, because the data in itself is not that big. The output of the joins is relatively big, but we can take advantage of the map side joins, which are very fast. And the output of this join looks roughly like this. So I told you that we are using protocol buffers. So you will have this nested protocol buffers where like the overall one represents one pair of two users. And then inside that you have a protocol buffer which represents the user, another one for the candidate, and then some with features which are about the pair as it is, for example, distance. Right? And now we need to score and predict how likely are these two people to actually be interested, right? So we run this through the models that we have trained offline, and we predict the probability for each of them. Unfortunately, this is a very embarrassingly parallel process, so we can run this in parallel on the Hadoop cluster. So that helps us basically score all the potential pairs, and if you have millions of users, million times million is a lot, so Hadoop helps. I mentioned that we use our DSL, which is written in Scala, that helps us express these kind of features which are predictive of communication between two people, and this DSL is nice in the sense that, when we come up with a new feature which is predictive, we can just implement it. We write a little snippet of Scala code which lives inside a JSON, which is the specification of the model. We just push it into production, and there is no real code integration. So here you have an example of is the religion of the two people the same? The second example is who is drinking more, the female or the male? And the last one is, is the male living close enough to the female so that you would consider dating him, right? So here he is lucky because he's within 60 miles. So this is the affinity system, right? So now we know who is compatible, and now we know how likely they are to talk to each other. So we still need to make a lot of decisions. We need to decide who to introduce to who. As I said, we don't want to overwhelm users by just showing them a few thousand results, right? No one is going to seriously get to know 1,000 other people, and then they will probably fall back to just looking at the photo and screening based on that. So this distribution problem can be thought of as you have this set of women, set of men, and there is a bipartite graph between them. So these edges are present if the two people are compatible. So that means, our definition of compatibility is they have a super high chance to be in the upper quartile in marital satisfaction. So there are a lot of edges missing here, which are people, maybe they could have potentially a happy marriage or average marriage, but we only introduce people who have a very high chance to be in a very happy marriage. And let's say for the sake of illustration here that, people would be overwhelmed if they got more than 2 matches, right? This is just for illustration here. So we want to deliver maximum 2 matches to each person. Then you can augment this graph, and if you imagine that each of these edges has a capacity, the ones on the sides have capacity of 2, which and the ones in the middle have a capacity of 1, and you would run a Maxflow solver on this, it would come back and tell you which people you should introduce so that you introduce the highest number of people. However, if you label the edges as well with the probability that they are actually like each other, which is sort of a quality of the match and the chances that they will be interested, then you can solve this as a transportation problem. And then what you get back is the matching in that graph, which maximizes the total expected amount of communication in the whole graph. So you can choose the matches like this, and then you see that each of the people got 2 matches. But to the user, it looks very transparent, right? Adam here has been matched with, a few ladies, and he doesn't know anything about this complicated machinery which is running behind the scenes. So let's say, he has these matches, all of them are compatible, and they also have been selected so that there is a highest chance that he's interested in them and they will be interested in him back. So let's say he likes Julia here at the top. So what does he do? He can message her, and we have a system we call guided communication, which you can decide to skip, but it's very helpful, especially for people who are shy, or even for people who are not shy, but it helps to build a shared context. So by the time Adam and Julia reach what we call open communication, where they exchange phone numbers, they are ready to hit their local Starbucks, and they have something to talk about there. And as you might have guessed, Adam and Julia are a real eHarmony couple. They actually got married. And there are quite a few marriages that start on eHarmony. In fact, in 2005, that was about 90 eHarmony members were marrying every single day. So how we get into these numbers is we ask an independent company, Harris Interactive, which is specialized in surveying, and we ask them to go out and sample married couples around the United States. And they then come back and tell us, well, this is the estimated number of marriages, based on our sample, how many meet on eHarmony, how many meet elsewhere. So and then when we did that in 2007, it was already 236 people every single day. In 2009, it was 542, which at that time was about 5% of all US marriages. So this is pretty impressive, but you might ask, like, this is a lot, big numbers, but are the people actually happy? Fortunately, we have data on that now, too. So beginning of June, there was a study done by a team led by John Cacioppo, who is a professor at University of Chicago. And so they analyzed a sample of data like this collected by Harris Interactive. This data basically sampled people who got married between 2005 and 2012, right? So pretty big period of time. And they were looking at, are the people happy, where did they meet, et cetera. So this study was published in Proceedings of National Academy of Sciences, which is one of the top cited interdisciplinary journals, and got a lot of coverage. Like, these are a few venues that covered it within the first 24 hours. And there are a few interesting takeaways from that study. So one surprising thing is that about a third of the couples that met in this period, 2005 to 2012, met online. So that surprised even me, even though I was a believer in this way. So a third of people who married between 2005 and 12 met online. And it turns out that the people who met online actually have a lower rate of divorce or breakup than the people who met through more traditional means, right? At work, through friends, etc. So there was about 6% divorce rate on the people who met through all the online ways combined. One encouraging thing for us is that about a quarter of the people who met and married through online dating came from eHarmony. So eHarmony is responsible for a quarter of the marriages coming from the dating space. And that's very impressive because there is hundreds and hundreds of, maybe thousands of dating sites out there. And the most encouraging thing is that the couples that actually met on eHarmony had the lowest divorce rate. So they had below 4% divorce rate compared to all the other ways of meeting. Thank you very much. Thank you. Yes. Yeah, I see a question there. Yeah, maybe can you say that on the microphone so that it's recorded for the video as well? Thank you.
So I got actually a few questions. So first question is, how do you solve the cold start problem? When a brand new user comes to the site, you don't have time to run the MapReduce job. So how do you solve that? Yes. My second question is, you mentioned for Affinity, you're doing a million by million. Are you really doing a cross join, or you're optimizing it a certain way? And I'll ask my third question and then I'll get out. How do you get the feedback loop? So you do the recommendation. How is that going back to the model? How are you solving that? Thank you.
Okay, thank you. So we have 3 questions. If there are more questions, even if we don't have enough time, I see quite a few, tweet them at me also if we run out of time, but I will try to answer as many as possible here now. Okay, so the last question was about the feedback loop, right? And can you remind me?
So first was cold start.
Okay, cold start.
And second is, are you really doing a cross join?
Oh, the cross join. Okay. So in terms of cold start, it's very important to match your new customers well, right? So if you use, for example, collaborative filtering, which is widely used, for example, for movie recommendations, right? We saw a presentation by Netflix. You need some feedback from the users what they liked, and you might present, some movies to people, and everyone has seen some movies, so they can express that. But it's a bit hard to elicit that in a dating setting. So from the start, we have been focusing, actually, we were starting from the cold start problem, and a lot of our features are sort of content-based or, metadata-based. So we have these thousands of data points about each user, so even if you come in and I have no idea about your preferences, I can already predict pretty well for you who you will be interested in. Because I know your ethnicity, I know your age, I know your religion, I know where you live. I know also a lot of things that you specify that you want. You might have said, I'm not willing to drive more than 30 miles. So all these things we take as input features for the machine learning algorithm. We don't necessarily obey that 100%, because in our experience, what we have seen is that if you say 13 miles is max, you would be okay with 31 miles if it is a very good match. So we might relax that restriction, grab a little bit more people, and then rank and score them based on the probability of communication. And then we deliver those, and we mark them that this is something where we might have not satisfied exactly that. So I think we have pretty well covered the cold start problem here. Because there is a lot of features, the questionnaire is very long, there is a lot of behavior that we can observe on the site already. Okay, so then there was the question of the feedback, right? So on the side, we observe the behavior of the user. So as you interact with the matches, you can close them, you can communicate to them, you can send an icebreaker, you can communicate to them to a certain stage and then close it up. And all this information is captured and available to the models, right? So we have a lot of powerful features which are derived from the user behavior, who they communicated to, which are contributing to the model. So as you are using the site and communicating to other people, the matches that you are getting should be improving, right? And there was a third question, which was?
So for the affinity calculation, are you really doing a million by million cross?
Okay, yes, exactly. So it's not really, million times million is a lot, right? So even if you run this on a Hadoop cluster, it would take a while. We would probably not make our SLA till the morning. The fortunate thing is that, people are not willing to go for the perfect match on the other side of the planet, typically. Because there is no guarantee it really will be a perfect match, even if the algorithm will say that. And then, so there is a very low probability that these two people will be interested, unless, of course, you specify that you want anyone in the world, and this is sort of a small fraction of the people. So fortunately, already people tell us how far they are willing to travel, what kind of, drinking and smoking preferences they are okay with, etc. So this prunes it down quite a bit, yeah? But as I said, we don't take this, as the hard rules. We actually expand it, and we score much more than the people are saying that they are looking for. Okay, thank you. Yes.
Fascinating talk, very, very interesting. I just had a question. Given that the whole process is data-driven, are you able to identify dishonesty in your data and counter for that?
Yes. Thank you. Thank you. So, yes, dishonesty has been reported on many dating sites where people try to present themselves. So, we try to help our users to present themselves in the good light, yeah, but we don't try to encourage them to lie or anything like that. On the contrary, we set up the incentives. We set up the incentives in the system so that it is in your best interest to actually provide truthful information about your preferences so that you get good matches. So, and also the process of going through the big questionnaire at eHarmony, there is a quite high cost to invest. So we find that typically people who are a bit dishonest and maybe are into shorter term relationships will rather go to other dating sites where they don't have to go through this serious screening. There are some things that you cannot really, like if someone wanted really to lie, they could, but then they can be uncovered very quickly and our users can flag users. And there is a last technique that you can use, which is, in the questionnaire, it's possible to disperse like some questions where there is obvious what should be an honest answer for everyone in this room, right? Like, is it true that you are sometimes angry with other people? Right? Oh no, never happened to me. Like if you have like 10 questions like this interspersed there, and you see someone always answering on the extreme unlikely case, then they can be flagged as inconsistent in their answering, and we cannot trust the other answers. And then we refuse to a small percentage of people, on the side. We ask them to retake the questionnaire, or
Yeah, interesting.
Thank you. Thank you.
Okay. In terms of data disambiguation, how do you guys deal with what may look like noise but may not be noise? Let me give you kind of an example. Let's say one person says, I like Ford Mustangs. Another person says they like Harrison Ford. A third says they like Gerald Ford. So one person is a car person, the other person is a movie person, the other person is a political person, but they all have the word Ford. How do you deal with those, one example of multiple disambiguities that have rich information but may look like noise?
Yeah, thank you. So yeah, this is an inherent problem, and like you always encounter this when you are dealing with free text data. The thing is, when you are empirically driven, what you can do is you can come up with a crazy feature. Maybe it is like, did they both say Ford, and I don't care which meaning? And then you can empirically evaluate whether the people who both said Ford actually are interested in each other, right? So if that feature is just too noisy, it will not make it into the model. And of course, if you have some semantic annotation on that, you will get some extra mileage out of your features. But what I find very often, already like the first approximation gets you about 80% of that, of that lift.
So your key vector variables really drive the model, and that stuff just gets treated basically as noise overall.
Yeah, it's an empirical approach where you can throw anything in, and then on your holdout set you test whether it actually is useful. And often you would be surprised that some things that you might be sort of random actually are very predictive. Yeah.
Okay.
Thank you. Yes. So, sorry. Yeah. Actually, can you say it into the microphone, please? Yeah. Yeah.
I actually have like a follow-up question for that one. So you said you can empirically evaluate your feature, but given that you have like 1 million features, how can you empirically evaluate all of them?
How can we select the features which are predictive?
No. My question is actually a follow-up question for the previous question.
Yes.
So he mentioned that like 3 people all mentioned word Ford. So you said you can actually like empirically evaluate like the feature Ford by like looking at the result and see if that Ford thing is really a noise or it actually matters. But the thing is like you have 1 million features. How can you empirically evaluate all of them?
Yes. So okay, so the idea is here you can come up with a lot of features, and how do you choose the ones which are predictive? I think this is more general than just like for example for free text, but you can come up with a lot of features, and how you choose the ones which are predictive, right? So there are techniques like L1 regularization, which help you, sort of build models which are sparse, assuming your underlying, mechanism is actually sparse, that there is only a limited number of features which matter. Often you have some prior knowledge of what kind of features might be predictive, actually. So, you generally start with those features, you build a model, and then you see what could predict the residuals. But yeah, like in general, in machine learning, this is an open problem, right? If you have loads and loads of features, much more than you have data points, it's still not clear how to do this best, but there are techniques how to select from large number of features, like the L1 regularization. And we actually have a lot of data because, we make, hundreds of millions of matches, every day. So this accumulates over time, right? And generally, you have a distribution where some features are very frequent and some very infrequent. So that helps you. So you will have some data for the more frequent features. And of course, you are limited. You cannot come up with you know, the importance for some very, very rare features which you have seen only once. Thank you. Thank you, guys. So I think we are out of time for the questions. I'm sorry if you come, if you want, come after and we can talk offline or tweet it at me. Thank you.